welcome mindsetters to this session of Learn Extra Live for grade 11s. I'm Ty and I'm here with Dina, who's going to be taking us through today's lesson. Dina, what are we doing today? How are you?
Hi everybody, I'm very well, thank you.
Good.
We're doing trigonometry. We're revising all the standard trig, those little tricky bits that you often feel it's difficult, not quite difficult. So if we revise it, I'm sure you'll find it easier.
All right. So, Dina, while you make your way across the Anyway, mindsetters, make sure you get on the page. That's what I was trying to say. www.facebook.com/learnextra. Get chatting to me. Let me know what you guys are thinking. Oh, yes. Yes. You know, it's a Monday show. So we're giving away this awesome Casio calculator and this labeler. So make sure you get on the page. Because if you don't get on the page, you basically can't win these awesome prizes. So make sure you keep talking to me on the page. And I cannot stress enough that you guys need to use this as a forum for you guys to chat. And I always say, mindsetters, if you see a mindsetter in trouble, just help them out. Don't just sit there with the information if you know you can help out. That's the point of the Facebook page. You need to talk to each other. And on that note, I also want to make sure that you guys know that you need to tell a friend, as I always say, to tell another friend, to make sure that they get on the page and also join in and get chatting with us. And don't forget, you guys can also work together in groups. Make sure that you guys just hang out, work together in groups, watch the show, post up on the page, and let us know what you guys are thinking if you guys are enjoying the show. But then on that note, this is why I want to say thank you to Liberty for sponsoring. And this is why I hand over to Dina. Dina, take it away.
Thank you, Ty. Well, we said we were going to look at the trigonometry revision, and there are three basic foundational concepts that we need to understand when dealing with grade 11 trig, which will be also the foundations for grade 12, and that is being able to work on the Cartesian plane, being able to work with angles that are rotating on the Cartesian plane, being able to use the reduction formulae, and being able to solve an equation. And if you really have got those three well grounded, then you shouldn't have a problem in grade 12, because we just add further topics onto the reduction formula, onto the solving the equations, and also being able to work on the Cartesian plane. So let us have a look at some of the work that could appear using the Cartesian plane. I'm going to start off with a question. We have a given expression, cos 65 is equal to m, and we also given that cos theta equals to m. And the question is, give two possible values for theta if theta is between 270 and 360. Now, you may have come across the fact that in order to draw a diagram that fits this description here of theta being between 270 and 360 degrees, we don't use a triangle to place that theta in, because the angle is larger than 270 degrees. So what we do is we take the Cartesian plane, which defines angles from 0 through to 90, through to 180, through to 270. And once they've completed a complete revolution, we talk about 360 degrees. So we then place a quadrant 1 angle by rotating from the 0 degrees, and we rotate all the way to 90 degrees in an anti-clockwise direction. And therefore, an angle that is rotated, theta rotating anti-clockwise, will always be a positive angle. Okay, so I'm going to be rotating from 0 degrees all the way to 90, 180, 270, 360. These are known as your quadrant angles. So they are angles that are rotated which are perpendicular to the axis. So those are known as quadrant angles. But if we're given that cos 65 is equal to m, what we're really saying is that we've been able to rotate through to a position theta, where that is now 65 degrees, and that position, let's call it P, where it goes from the origin OP, has got a ratio of m over 1. And so we know that the x value is m and the radius is 1, because the definition for cos 65 in the Cartesian plane is that it is the x value over the radius after that ray OP has rotated. So OP is known as the radius. So OP is 65, and the question is, we need to give two possible values where we would be getting exactly the same ratio. So same ratio, what can theta be to give us that same ratio? Well, I'm going to work with this OP, because what you're really saying is that for the angle to be in this position, which if you look at it would be quadrant 4, so that would be our traditional quadrant 4, it would mean that this rotation would go all the way through to this value here, or this green value here, which is 360 minus this little bit here. So this green angle is essentially the same because my radius is the same and my x value is the same. So because that's true, then the cos of the green angle will be the same. So therefore this angle here must be 295. But they've asked for two angles in that quadrant. Basically, that's the quadrant. And the second angle would be this one here, which is now rotating in a clockwise direction. So if theta rotates anti-clockwise, we've got a positive angle. But if theta rotates rotating in a clockwise direction, then you would get a negative angle. And so this angle here that rotates to the same x value would be negative 65 degrees. Now you could also get a multiple angles, because we could rotate from the green, we could rotate once and a second time. So that would then give me this orange angle would simply be 295 plus a full revolution of 360. So that angle would be 655. Okay. This green angle and the purple angle are what we call coterminal angles. So they have the same terminal ray. The ray that they're sharing ends off at the same position. Hence the rotation towards that. Different rotations, one is negative, one is positive, but we talk about the angles being coterminal. They're sharing that same ray. So three things that are important. One is to establish where the quadrant angles are. Two, to establish what size the angle is rotated to understand that every single positive angle has a coterminal negative angle and vice versa, and that if you add the two values, you'd get 360 degrees, and that you can generate an infinite number of angles that will be coterminal, because you can add on revolutions of 360, and so you're generating angles which to us don't really make any sense. They're quite abstract. They are theoretical angles that we can produce, but purely practical, you wouldn't actually be able to see them, because you're actually talking about an angle that's larger than 360 degrees. So a negative angle also is a theoretical angle. It's an angle that's measured in the opposite direction, and convention, mathematical convention, is that you measure angles in an anti-clockwise direction. So that would be the Cartesian plane. Now, let's have a look at, possibly we could use the Cartesian plane here, but let's first see what the setup is. Sine 16 is k, and we have to write in terms of k what sine 196 is. Now, what I'd like to do is to first of all really work on what the meaning of that is, so that we kind of understand what is being given. Because it's sine 16 and it's in 16 is an acute angle, you could use a triangle to depict the information around what sine 16 would look like. Sine 16 would come from a right angle triangle where one of the angles is 16, and since this is k over 1, we have that the opposite side is k, the hypotenuse is 1, and therefore the remainder must be the square root of k squared actually the other way around, would be 1 minus k squared. So it would be the hypotenuse minus that side squared. So using Pythagoras, I can always find the third side. So I don't know what these values are, but I could on the calculator find out what the sine of 16 is and get a value. However, with this question, you're writing it in terms of k. And so a further instruction would be that this has to be without a calculator. Okay. So now we need to establish, right, sine of 196. 196 can never be written on that triangle. 196 is in fact larger than 180, so it's a reflex angle. So how do we utilize our information to be able to express what sine of 196 is? Well, that little tool that you carry around with you, that little very important Cartesian plane that you carry around with you, has got quadrant angles, 90, 180, 270, 360. And the other thing it has is that any angle that's larger than 90 degrees can be written in 4 different forms. It can be written as a supplement. It can be written as a reflex angle of 180 plus, and it can be written as a reflex angle of 360 minus. Further than that, we can also utilize what we call our cofunction if necessary. So remember I said there are 4 ways of writing this. We can write every function as a cofunction. So before we jump there, let's come back here and see what would sine 16 be as the cofunction. Well, the other angle that's missing is this angle here, and that would be a 74, not a 64. So let's fill in 74 degrees. So we've got the complement. So what would be the same as k over 1? Well, in this scenario, I'm using 74, and that's adjacent, and that's hypotenuse. So it would actually be equal to the cos of 74. So we often talk about the theoretical understanding of cofunction, the fact that the complement and adding or taking away a CO will give you the same value. But you can actually see it very clearly on this triangle, how to take the cofunction of 16 means to change the position of side k, whereas here it was opposite 16, here it's now adjacent to 74, hence cos 74 gives us exactly the same thing as sine 16. So to be aware that every single trig ratio of an acute angle can be written as a cofunction, and that comes in quite handy when sometimes we're stranded and there's not much else we can do. So we've got that little tool I mentioned, where we can rewrite angles in quadrant 2, 3, or 4, and then also utilize a cofunction. So 196, you would first start and say, well, that's bigger, that's over here. So it can be written as the sine 196, exactly the same thing as 180 plus 16. Okay. Then there is one other thing that you carry around with you, and that would be that in this quadrant, all my ratios are positive. My ratios are positive for sine, my ratios are positive for tan, and my ratios are positive for cos. So when I have sine of 180 plus 16, I'm sitting with a negative ratio because only tan would give me a positive ratio. So this one reduces to, my next thing is to address my sine, which is negative, and then I get sine of that acute angle. So if I take sine 16, it's going to be k over 1. So it's going to be that k over 1. But in this case, because it's in the third quadrant, it's going to be minus k. Right, so to recap, you would be taking let's just go back there. Sure, okay. Okay, that's very, very odd. It's just disappeared. You would be taking the 196 as firstly its position, so third quadrant. Then you'd be writing what the angle can be written as, which is 180 plus. And the third thing you do is to say, well, is that sine well, is that ratio positive or negative? So you would address the sign, SIGN, of those trig ratios. And with that, you would have been able to rewrite it in terms of the given one of sine 16. So you ultimately is what we call reducing or using reduction formulae to be able to get to a reduced version which gives you the same ratio. Okay, back to
Do
time.
you want to take a quick ad break?
Yeah.
Alrighty. So mindsetters, make sure you get on the page. Let me know what you guys are thinking. Talk to me, talk to me, talk to me. I'm seeing your questions coming in. So I'm going to make sure I'm going to look through them, and hopefully we can get through them to in the next session. But for now, I'm going to see you after this break. And welcome back, mindsetters. Hope you had a nice little break there. I know it was really short, but that's because we need to bring you back this content. So make sure that you guys do not disappear anywhere. You need to have your pens, pads out and making notes. And yes, I'm scanning through the page right now, and I'm going to be looking for the awesome winners for this Casio calculator and this labeler. So make sure you guys keep posting. But for now, this is where I hand over to Dina. Dina, take it away.
Thank you, Ty, and yes, welcome back. We were using reduction formulae to work out various trig ratios by using a given one of sine 16. And we got to sine of 196, and I'd like to see some more questions. Well, the next one was cos 74, but we spent quite a lot of time working with cos 74 and talking about how cos 74 is the cofunction. So therefore, if you were given cos 74, we've actually said that that's just equal to k. So that one's sorted out. Let's rather have a look at something more interesting, something like sine of negative 344. What would you suggest that we do with that kind of angle? Let's analyze it. What kind of angle is it? It's a negative angle. So you know how it's measured. Which quadrant would it lie in? Negative 344. Well, there really are two ways of going about this. One, you could look for the coterminal angle, or two, you could use the rule for negative angles. And when I talk about the rule for negative angles, I'm really saying that if you have the sine of a negative a, that is the same as negative sine a. So if you change the sign of the angle, you change the sign of the ratio. That's basically what's happening. So sine of negative 60, for example, would be negative sine 60. The two are equivalent. Tan of negative a exhibits the same rule. So that's also equal to negative tan a. However, cos of negative a is the same. Can anyone guess why that is true? Why, if you change the size of the angle or the sine of the angle in the cos function, that the ratio is the same? Well, simply because of the nature of the cos function when you sketch it. When you sketch it, you'll find that the function is symmetrical about the y-axis. So it's a mirror image on the negative side, which means that sine 60 is equal to sine of minus 60. So the only two functions that are not symmetrical about the y-axis would be sine and tan. And if you change the sine of the angle, you change the sine of the ratio. So you could use that rule if you wanted to. And we're going to do both. So this could be the same as sine, actually negative sine of 344. Because what we're doing is applying the rule that says that if we change the sine of the angle, we change the sine of the ratio. And then you would now be back into quadrant 4, so 360 minus something, so it would be negative sine of 360 minus 16, so it would give us positive sine 16. Okay, did you catch that? Sine of 360 minus 16 is quadrant 4, which would give you a negative ratio, but you already have a negative to take into consideration, so your ratio would then be just positive sine 16, which is k. Now, the one I'm really interested in is how you can check that. Okay, so we've just followed a very theoretical route. We've used the rule, we've used the reduction formulae, and we've got it as sine 16. How could we check that? Very easy. If we take my quadrant and we say that to get to this angle, we basically have to rotate in an anti-clockwise direction. So this becomes my negative 90 quadrant angle, my negative 180, my negative 270. So can you predict which quadrant this is sitting in? We're going to rotate from 0 all the way through to this quadrant there. So this angle there is negative 344, which means what? That this angle here is the coterminal angle. And if that angle is the coterminal angle, that can only be positive 16. Hence, the result that my whole thing came to sine 16. Now, isn't that wonderful how that all matches and aligns, and you're able to verify that, in fact, what you were doing is actually 100%. So sometimes it's useful with a negative angle to theoretically find the ratio, but then also to plot it on a little Cartesian plane as a matter of just checking, just verification. That's all. You're reasoning that if that is my angle that has been rotated, then there's got to be a coterminal angle which share the same ray. And because they share the same ray, the x, the y, and the r values will be the same. Hence, that ratio doesn't change. So the size of the angle is changing, but the ratio remains constant. Okay, so that was a negative angle to consider. Then we've got this let's just get to the page. Okay, let's just extend the page. There you go. All right, we've got this 1 minus cos squared 164. Well, there's lots happening here. There's a squared function, there's a 1 minus a squared function, and there's a 164. How are we going to deal with all those things? Okay, firstly, let's deal with the 164. We always, in Trig, in order to reduce things, we always reduce to an acute angle. It makes matters much easier. So 164, do you agree, is just 180 minus 16. So the position of 164 would be a second quadrant angle. And now I'm going to deal with this one step at a time. If I say cos 164, what is that equal to? What does that reduce to? Okay, if we draw our little diagram, we've got our quadrant angles, 90, 180, 270, 360. This is going to be with you all the time, A, S, T, C. This angle here is in the second quadrant. That means it equals negative cos 16. Agreed? We have a negative ratio in quadrant 2 for a cos ratio. Great. Now, if I say cos squared 164, what I'm really saying is that I've got to take what my linear, negative cos 16, and I've got to square the whole function. So I'm squaring that whole function. What happens? A negative cos 16 times a negative cos 16 equals cos squared 16. So any function that is squared, although its linear reduction can be positive or negative, when you see that squared, it's always going to yield a positive product, because a positive times a positive is a positive, and a negative times a negative is a positive as well. So you could go through these 4 steps in order to get there, but you as grade 11s mastering numeracy would agree with me that we could go from this step all the way to 1 minus cos squared 16 without worrying about signs, because it's a squared function. So a squared function just reduces into that acute angle without worry about signs. But if it's linear, we need to worry about it. And if it's the power of 3, we need to worry about it as well, because odd powers will yield negative products, but even powers do not do so. Okay, so any ideas as to what we could do with 1 minus cos squared 16? Well, some of you may be saying, let's use a diagram, which we've already drawn up at the top. We've drawn a little function here. So cos 16 would just be that over 1. So we would now take 1 minus that, okay? And that's a pretty good way to look at it, using a diagram. The other thing would be, some of you may know that there's a square identity. Actually, you should know by now that there's a square identity of sine squared plus cos squared is 1. So that 1 minus cos squared is just equal to sine squared. Okay. If you didn't know that, then we could rewrite this. 1 is the same as sine squared theta, or in this case 16. So that would be 16 plus cos squared 16. So 1 can be written as the square of both sine and cos together, and then we are subtracting cos squared 16. So we get sine squared 16. Now, using a diagram, that would look like this. 1 minus, remember, we worked out that if this was 16, this was k, and this was 1. Using Pythagoras, this side would be 1 minus k squared. So this would be 1 minus the root of 1 minus k squared over 1. And I'm taking it all the way from here. So I'm replacing cos of 16 from this picture here. So I've got to square my cos, and then I'm left with what? That's equal to 1 minus, if I'm squaring that, I'm left with 1 minus k squared all over 1. So that is equal to 1 minus 1, which is 0, plus k squared, and sine squared 16 was also just k squared. Okay. So treating identities, dealing with identities, and establishing the links if you do have that right angle triangle so that you can use the ratios at the same time. Wonderful to have two ways of checking work. You build your confidence through that when you are able to check something and not just leave work to a friend or to somebody else to check. Right, let's look at our next slide. Having a fraction. So that question, sometimes you'll get a easy in question. Well, I just ask you some simple, straightforward trig ratios. Here we've got a fraction that we'd like to simplify. The question is simplify without a calculator. Let's scan. I like to just look at what the angles look like. I've got a negative 120, negative angle. A 660, angle larger than 360. A 40, that's already acute. I'm not going to touch it. And I've got a 410, also an angle larger than 360. And we've got to reduce. Now we can't do this by ourselves. We need a little diagram to help us out. So it's 180 minus, 180 plus, and 360 minus. We need this all the time. Right, so we now have sine of negative 120. It's your preference. Would you like to find the coterminal angle, or would you like to just take the negative angle rule? Up to you. I'm going to use coterminals because I like working with positive angles. So this would be the same as the sine of 240. And this would be the same. You would take your calculator and you would say 660, and you would take away revolutions until you got to an angle that's smaller than 360, and that would give us 300. So that would be the cos of 300. And in the denominator, I'm going to leave acute angles until I know what I would like to do with them. For the time being, sine squared 40 is great. 410 would be, we would take 410 whenever it's larger than 410 minus 360 would give us 50. So that would be sine squared 50. And we're now ready to say that 240, this time around I'm not going to write them down, I'm going to do them orally. 240, quadrant 3, it's 180 plus 60, so this is the same as negative sine 60. Times the cos of 300, that would be fourth quadrant. Cos is positive in the fourth quadrant, so it would be just times the cos of 60. What have we got in the denominator? Well, I notice that 40 and 50 are add up to 90, so they are complementary angles. So if I change this one to a cos squared 50, can you see what will happen? Very interesting. I could get it to a cos squared 50 plus a sine squared 50. And what does that give you? Okay. Then you would just use your special angles with sine 60. You'd have sine of 60. Your calculator gives it to you. Oh, that doesn't really help, does it? Let's give ourselves 60. And we've got root 3 over 2. So we would get negative root 3 over 2 multiplied by cos 60, which is a half, and we'd have this 1 in the denominator. And that gives us negative root 3 over 4. Okay, and so there was a classic example of about a 7 to 8 mark question where you have to reduce and then use the special angles. Also, the moment you've got squares, you know you're working with the square identity. Back to Ty.
All right. So mindset is just I'm looking through the page. I'm just saying, man, I'm loving it. I'm loving you guys posting. I'm loving it, loving it. Just want to say to those of you who are writing soon, if you've got even like one of your class tests or a cycle test, just want to say best of luck, especially Musa. I saw your post there. Just want to say good luck. But for now, guys, make sure you get on the page and chat to us. But for now, we'll see you after this break. Welcome back, Mindsetters. Hope you had a nice little break. You did whatever you had to do. If you had to go take out the trash, you took it out, or you had to go cut onions, whatever. I said, oh, I've got a thing like against onions. The smell, crying. But anyway, that's besides the point. You need to get on the page, start chatting to us, let us know what you guys are thinking. If you're lost, if you need help, post, and let us know. Because yes, I still need to give this stuff away. So yeah, please make my job easier and just post. But anyway, on that note, this is where I hand over to Dina. Dina, take it away.
I think onions make you cry, but trig doesn't, because trig's easy, right? Especially when you do learn extra. Right, folks, we have done the Cartesian plane, we've done reduction of formula, so what's left? We're going to do some solving of equations now, and then in the last little bit of the show, we'll look at proving an identity, and just looking at how sneaky that identity can be. So let's get straight to it. Let's have a look at an equation, and let's find the general solution. The equation is, we don't have to have this here at all. We have, if cos of A plus 40 degrees is equal to 0.32, find the general solution. Now, oftentimes they will say find A, where A is in between a set. We don't actually look at that at all until such time as we find the general solution. Our priority is to find those formulae that will yield many angles. Now, earlier on, somebody posted a query on why is cos of minus 60, why is that the same? And whenever you've got a why question, that's always fantastic because there's got to be a reason for it. And the best way to reason is to try and draw a diagram that will give you the given situation and where you're going. So try and draw something. The best possible way to draw that is to actually get a function going. So you would have, for example, cycles and cycles and cycles of this cos function. And you would have this on either side of this y-axis. Now you'll notice that if I find a particular y value, if I say my y value is this much, do you agree that at this place here, okay, you've got, let's say, 60 degrees. Let's say this was a half. But exactly on the other side, you've got a mirror image. So what we're saying is that cos 60 is the same as cos of negative 60. That ratio, that blue value, is the same in both cases. And that's simply because the cos function is reflected about that, is reflected about the y-axis. So because there's symmetry about the y-axis, whatever's on the one side, the y value is going to be the same on the other side. Very much like your parabola graph as well. It exhibits that kind of symmetry. So that is really the reason for that happening. Now, what we're trying to do with the general solution is we're trying to find if this is 60 over here, what is over there, what is over there, what is over there, and what is on this side. Okay? So all those green values. And at the same time, we're trying to find what are all these purple values. Okay? And I've just stopped because my board stops. But the bigger the board, and if you had to zoom in, you'd keep on getting values to infinity. And that is what we mean by general. It means all the possible values that you could get. So we can get how many greens? An infinite number. Give me a formula for that. How many purples? We can get an infinite value. How do we get them? So that is really what our general solution is. Now the sine and the tan graph, for those of you wondering what happens with sine and tan, go and draw it. Go and draw your sine curve and draw your tan curve. Is it symmetrical about the y-axis? If it isn't, then the cos or the sine of 60 is not going to equal to the sine of negative 60. And it actually isn't, because it's only the cos function that actually exhibits this kind of symmetry. So to find the general solution means to go and find all the greens, all the purples, find the two formulae, and from those, once we've got the formulae, then we are going to find particular A's that will be inside that set there. Okay, right, so I'm just going to erase this, and I'm hoping the person who posted that question has now got a better understanding of why cos 60 is equal to negative cos. Right, and so the general solution for cos is that whatever value you are given, a plus 40, is going to be equal to your calculator angle plus periods of 360 degrees. Or a plus 40 degrees is equal to the additive inverse of the calculator angle plus k360. So what you're saying is whatever this angle is, this angle here, it gets written as the angle that you're searching for, or the second formula. And this is how I've constructed my general solution. Okay, I will always be giving you two formulae if I'm working with sine and cos. There's got to be two separate ones. A plus 40 is a calculator angle plus K360, or A plus 40 is minus the calculator angle plus K360, which means that we've got to go and fetch that calculator angle. So if we do that, we've got closing layer. Let's just move it along. Okay, we've got the cos of a plus 40 is 0,32. So because it's a cos function, I'm going to have my yellow button to give me the angle, and it's a 0.32. And what angle does it give me? Well, it's giving me 71,3. So that 71,3, I'm now going to have as 71,3 plus K360. Have you solved for A yet? No, we haven't. We still have A plus 40. So in order to get A, I now have to take this 40 over. So it's 71,3 minus 40 plus K360. What happens on this side? Same thing, but it's the negative of that, because we've said that the negative angle with a coterminal is in quadrant 4. So A plus 40 is then minus 71,3 plus K360. So A would be negative 71,3 minus 40. That doesn't look so good. Let's just fix it here. This looks like a plus. Let's just fill it in as minus 40 plus K360. And somewhere in your calculation, what is K? K, they are multiples. Let's put him in here. k are multiples of integers. They're not fractions, they're not decimals, they are integer values. So A will then be 71 minus 40 is simply 31 plus k 360. We've now found one set of a formula that gives us a set of values, or A can also be negative 111, comma 3 plus k 360. Notice that when I was writing over here, I just wrote 3 dots to indicate that I haven't rounded off. I will only ever round off in my final answer. Okay, right, so this is what we call our general solution, that formula that will yield those infinite solutions. Once I've got that formula, now I go back to the original. Remember, the original said, find A so that A belongs to a particular domain. I will now test for k values, and I'll do that on my calculator. I won't write it down and waste paper. I'll just do it orally. If I have k as 0, do you agree this is 31, comma 3? If I have k as 1, then I've got a 360 plus a 31, which is too big. If I take 31 minus 360, I think we've got something there. So if we took the 71 minus the 40, and okay, so if we just clear that, and if we say 31.3 minus 360, and what does that equal to? Negative 3 to 8, comma 7. Okay, so it's negative, A could be negative 3 to 8, comma 7. So if I go 1, it's too big. If I go minus 2, it would be too small, and if plus 2. So I could only get one value from the side. What about this side? Well, if k was 0, then I'd get a value. But can you see if I'm minus 360 from it, I would get into 400, so it would be too small. And plus 360 over here, it would be bigger than 0, so I'm not actually interested in those values. So, or A could be minus 111, comma 3 degrees. So I'm actually getting 2 values that are sitting in that domain. Hence, I have found finite solutions for that particular set. So from a general, I've been able to narrow it down to 2 specific solutions. Okay, so that would be a general equation. Just summarizing for the trig, for all the trig, sine will have 2 formulae. Cos will have 2 formulae. Tan, because the period is over 180, we can find one formula which gives us all the tan values. So the tan would be your calculator angle plus k 180. Whether it's negative or positive, the calculator will sort out the angle accordingly. So tan is the easiest one to work with. I find cos the next one the easiest because it's either the calculator angle, as we had up here, or the negative calculator angle. And sine is the only one that's calculator angle and 180 minus the calculator angle. So the sine is the only one that actually requires some kind of extra arithmetic. General solution, always 2 formulae. Right, let's see if we can finish up with an identity. Okay. We need to prove that this left-hand side is equal to the right-hand side. And the best way when both sides need to have simplification is to actually split them. I often mark matric exams, and so many students lose marks because they don't follow the proof, the technical proof structure, which is to set out your left-hand side and simplify it, set out your right-hand side and simplify it, and see at which point they would actually be the same. So sine I can't do anything about, but as I've just spoken about the structure, I would take the left-hand side, and I would say it's the same thing as sine cubed, and I'm going to divide it by. I don't like working with what I call double-decker fractions, which means a fraction over a fraction. It's quite messy. It becomes organizing kind of 4 levels of fractions. Doesn't work for me. What I like is to take that division sign and to write a proper division and then see what the outcome is. So I'm dividing it by tan, which I already know is always sine over cos. So I'm automatically given a bracket to simplify. The problem with the majority of students, and I've seen this over and over again, is that the moment you see a division, you take the reciprocal, you multiply it, and you take the reciprocal of the first term that you see, and you take the reciprocal of the second. The reciprocal that you are taking, in order for the mathematics to be true and correct, has got to be of one fraction. So you're taking the reciprocal of two fractions, and if you do that, you're going to land up in a mess, because you and I are going to get different answers. So the key is, before taking the reciprocal, first get it to one fraction. So we've got, let's extend our page so that we've got a little bit more visibility, would be, let's get this to one fraction. So common denominator of sine theta minus cos theta times sine theta. Okay? And then I've got it down to sine cubed. Now that it's one fraction, I can take the reciprocal. So it's cos theta. And I can already see that there are two terms, so there's a common factor. Terms means there are factors. Okay? And then I sit and wonder, what happens now? Well, this sign can now go into that sign. So I'm left with a sine squared theta multiplied by a cos theta over a 1 minus cos theta. My next question is there anything in common between sine squared and 1 minus cos theta? Well, yes. We have that awesome identity which says that sine squared plus cos squared equals 1. So therefore sine squared is 1 minus cos squared. And the beauty of 1 minus cos squared is that it factorizes as the difference of squares. So lots and lots of powerful algebra happening here. So we have 1 minus cos theta times 1 plus cos theta multiplied by 1 over minus cos theta. Now, can you see how that goes in there? And we are left with cos theta multiplied by 1 plus cos theta. Okay. Now, that was the left-hand side. Let's see what's happening on the right-hand side. Well, we've spoken quite a lot this afternoon about how a squared function stays the same side. So we're not even going to go there. That's just cos squared theta, isn't it? And cos of 180 plus theta, third quadrant, so it's going to be negative. So that's going to be plus cos theta, because a negative times a negative is a positive. So my right-hand side is cos squared theta plus cos theta. What happened to our left? Well, cos squared theta plus theta as well. So that was also cos theta plus cos squared theta. So our left was equal to our right. Okay, lots of wonderful things going on there, and I'm hoping that you thoroughly enjoyed that. Back over to Ty.
All right, Mindsetters. I just want to say, wow, guys, it was a blast. Thank you guys for posting. And I just want to say thanks for Mo, and congratulations on that 93%. Mindsetters, if you have any awesome marks that you want to share with us, feel free to post on the page. I just want to say a quick shout out to Liberty. Thank you for sponsoring. And this is where I, as Ty, sign off and say thank you and see you next time.